Welcome to qnawire.
Consider the case of a part on a machine rotating at an initial angular velocity of 0.06 radians per second. We have omega I for the initial angular velocity is 0.060 radians per second. This part experiences an angular acceleration alpha of 0.70 radians per second squared, while it reaches its final velocity, omega f, of 2.2 radians per second. We are interested in finding out what angle the part rotates through while it's going from its initial angular velocity to its final angular velocity. And this will be delta theta. We begin by writing down one of our equations for the rotational motion of a rigid object. We have the final angular velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times delta theta, which is the change in the initial and final angles. Because we're interested in delta theta, we'll rearrange this so that delta theta is on the left and everything else is on the right. So we have delta theta equals the difference between the final angular velocity squared and the initial angular velocity squared, all over 2 times alpha, the angular acceleration. We already know that the final angular velocity is 2.2 radians per second, so we have that. We know that the initial angular velocity is 0.06 radians per second, so we have that. And we also know that the angular acceleration is 0.7 radians per second squared, and we also have that. Therefore, we have everything we need to be able to solve for delta theta. So we can plug these values in. For omega f, we have 2.2 radians per second, close the parentheses and square it, minus 0.060 radians per second, close the parentheses and square that, all over, whoops, let me redo that. That's better. All over 2 times 0.70 radians per second squared, and we'll close the parentheses. So this equals 4.84 radians squared over second squared minus 0.0036 radians squared over second squared, all divided by 1.4 radians per second squared. Now, before we do any further arithmetic, we see that we can cancel the second squared in both the numerator and the denominator, and one factor of the radians in the numerator, because we have radians squared in the numerator and only radians in the denominator. So this will give us delta theta in units of radians, which is what we expect since we're looking for the change in angle. So we find that this equals 3.45 radians, or equivalently, approximately 21.7 degrees. Now let's consider what would happen if we doubled the initial angular velocity, the final angular velocity, but kept alpha constant. So we'll rewrite this equation. Delta theta equals the final angular velocity squared minus the initial angular velocity squared, all over 2 alpha. But now we want to make sure we add a factor of 2 in front of omega f and omega I. And these are both going to be underneath the square. So we'll go ahead and write this all over 2 alpha, because remember, we're not doing anything to alpha, it's staying constant. factors of 2, indicating that we're doubling these velocities. Oops. So then this squared goes on both the 2 and the velocities. So don't forget that. We find 4 times omega f squared minus 4 times omega I squared over 2 alpha. We can bring out the 4. So we find that when we double the final angular velocity and double the initial angular velocity, but keep the angular acceleration constant, that we increase the angular displacement by a factor of 4.